Alright, so now that you've read the first few pages of Chapter 7, I want to give you a quick example of LU factorization and an example of how it can be used to solve a system of equations. Alright, so in the book they gave you an example with a 3 by 3 matrix, and I want to do another example because the one they gave in the book, they may have skipped a few small steps and expected you as the reader to kind of fill those in on your own. So instead of having you completely do that on your own, I want to fill in some of those steps for you. I'll do that with a smaller example, and then maybe you can go back and reread the example that they gave you and have a better understanding of what's going on. Alright, so here our matrix A, this 2 by 2 matrix, is with entries 1, 2, 3, and 4. The idea is to start, we want to multiply A on the left by some matrix that will kind of mimic the process of Gaussian elimination, or the process of row reduction. If we were wanting to row reduce this matrix, what we would do is we would multiply, or we would work on eliminating this 3 from the matrix, and so we would replace this matrix with row 2 plus -3 times row 1. And if I did that, then I would have gotten a 0 in this position where I have a 3 originally. Okay, now this matrix L1 is going to basically accomplish the same thing that your typical row reduction does that you learned in linear algebra. So let me just show you what L1 would look like, and it's basically, this -3 here tells us exactly what L1 needs to look like. What I'm going to do is I'm going to have 1s along the diagonal and 0s above the diagonal, and then if I put a -3 here in this second row, first column position, what that's going to do is when I multiply these two matrices together, it's going to eliminate the 3 from A and give you basically what you would have gotten after that first step of row reduction. Alright, so you can check this on your own. I went ahead and multiplied this out, and you can verify this. When you multiply these out, you get the matrix 1, 2, 0, -2. Okay. So this matrix right here, after one step of multiplying by this matrix L1, this matrix on the far right is what we call upper triangular, meaning that we have a 0 below the diagonal, and then you can have any other entries along the diagonal and above the diagonal. But the main thing when we talk about an upper triangular matrix is that we have all 0s below the diagonal. Alright, so this is what we call U standing for upper triangular. So what we have right now is we have that L1 times A gave us this upper triangular matrix. Alright, now our goal in LU factorization is to rewrite A as a product of a lower triangular matrix L and an upper triangular matrix U. Right now, all we have is the upper triangular matrix U. We still need to figure out what is L. But based on what we've done so far, if L1 times A equals U, A will equal L inverse times U. If I multiply both sides of the equation on the left by L1 inverse times U would be the same thing as A. So L1 inverse, let me write that down for you real quick. Again, in your reading, they told you that this is pretty easy to find out. Take L1, keep those 1s along the diagonal, and change the -3 to +3. So L1 inverse, in this case, is the matrix 1, 0, 3, 1. Okay, so this L1 inverse, notice this thing is a lower triangular matrix. It has entries in the lower half, but then above the diagonal you have zeros. All right, so this matrix right here, this L1 inverse, is going to be our L matrix. So A equals LU, where L was the matrix 1, 0, 3, 1, and U is the matrix 1, 2, 0, negative 2. So in the book, when they did this, since this was a 3 by 3 matrix, they had to multiply A on the left by a few matrices. They had L1 and L2, and multiplying by those gave you this upper triangular matrix U. And then to find out what your lower triangular matrix was, you had to do the inverse of L2 times L1. So look back at the book, reread that example, and make sure you understand that L is not the matrix that we have written here. This matrix here was L1. We use that to find L. L is the inverse of that. If we had multiple matrices that we used, L2, L3, however many matrices we need to get this matrix U that's upper triangular, L would be just simply the inverse of those matrices. All right, so I hope that helps make sense a little bit out of what they're doing in the book to find L and U. On the next slide, I'll give you a quick example of what they're saying at the bottom of page 135 about using the LU factorization to solve a system of equations. So let me just kind of quickly show you what they're talking about at the end of your reading on page 135 about how this LU factorization might be used in the process of solving a system of equations. So the system of equations we're going to solve here, we have matrix A from the previous slide times this vector x, and we want to solve for x, and we're solving ax equals b, where b in this case is the vector 5, 6. So you've learned how to solve this in linear algebra, and there's lots of ways we could talk about solving this. We could multiply both sides by A inverse. We could write the augmented matrix and do row reduction. There's lots of options, but what I'm going to show you with this LU factorization is going to kind of lead us towards some things that we'll talk about later in the chapter. The goal right now is to take some of the things that you learn in linear algebra and figure out how we can write an effective numerical algorithm, some kind of computer code that'll solve this system for us. And as we go through a chapter, we'll learn about some advantages and disadvantages of different approaches. And it turns out some of the things like finding the inverse of a matrix or multiplying both sides by the inverse of a matrix can be challenging in some ways. So let me show you what they're talking about with this LU factorization and how this can be used. So I've got AX equals B, and since A equals L times U, I can rewrite this as LU times X equals B. And what we're going to do is we're going to kind of group the U times X together. U times X, that's a 2 by 2 matrix multiplied by a 2 by 1 vector. That results in a 2 by 1 vector. We'll call that vector Y. All right, so this vector Y we can solve to find out what y is. Because if u times x equals y, then this equation that we're solving turns into just solving L times y equals b. Now, what we've done is we've taken our system of equations that we originally were trying to solve, ax equals b, and we essentially turned it into an easier system of equations here because L times y equals b. This will be easy to solve because L, remember, is lower triangular. Whenever you're dealing with a triangular matrix, then some of your process for solving the system can be shortened. So just to kind of show you what this looks like, L, remember, was 1, 0, 3, 1. And then I've got some vector y that we're trying to figure out. We're trying to find out what's y1 and y2, the entries in this 2 by 1 vector. We're trying to find this vector y so that when I multiply L by that vector, I get 5, 6. Now, if you look at this system of equations, this is a really easy system to solve. Let me just show you one approach we could take. Again, just if we want to do some row reduction, write our augmented matrix. It only takes one step of row reduction to get to this matrix here, 1, 0, 1, 0, 4, negative 4. Oh, sorry, I'm skipping ahead, I think. Oh yeah, 1, 0, 5, 0, 1, negative 9. All right, so that tells me that my vector y is 5, 9. Okay, you can double check that on your own. You can verify that if I do L, that's 1, 0, 3, 1, times y, that's 5, 9, then you do get the vector 5, 6. Okay, so we've solved for y here, and we solved it fairly easily because, again, the advantage to solving this equation is that L, to begin with, was lower triangular, and when it's lower triangular, it's easier to work with than, say, a matrix that is has entries on both halves, and the upper half and the lower half. So we're not done yet. Our end goal is to figure out what x is. We were trying to solve this equation ax equals b, but we solved a simpler equation first. We found out that if I want to solve Ly equals b, then y should be 5, 9. Now to finish solving for x, let's come back to this relationship that we wrote down at the beginning. We redefined u times x to be the same thing as y. So now let's return to that. I have u times x equals y, but y is what we just found, and u is the other half to our LU factorization. So now we've got this equation, 1, 2, 0, negative 2 times x equals y, which is 5, 9. Now again, this equation is fairly easy to solve because U is an upper triangular matrix. Whenever I'm dealing with a triangular matrix, then the solution process is a little bit more straightforward than if it were a full matrix with entries in the top and upper and lower halves. So again, you can solve this fairly easily, however you want to solve it, and we'll talk about our numerical approaches fairly soon, but right now, let me just show you, like, if again, if you're going to take the traditional linear algebra approach with an augmented matrix, then it would only take maybe 2 steps to solve this thing. First, I would want to turn this into a 1, so I'd multiply that second row by -1/2. And then I can eliminate this 2, multiply the second row by -2 and add. And what I end up with is -4 9/2. Okay, so again, there's lots of ways we could have solved this. We could have done back substitution. We could have used an inverse matrix. Again, don't worry too much about the method here for solving. The main thing to see is that if I'm solving an equation that involves an upper triangular or a lower triangular matrix, then it's fairly easy to solve. All right, so in the end, this gives us our vector x that we wanted. Okay, so going back to the original equation, we were trying to solve ax equals b, and now we know what x is. Now we know that x is -4 9/2. So something that's kind of lost in the process here, since this is a 2x2 example, it seems silly to go through all this work to solve this thing. So the thing I want you to understand about that is, yeah, it may be silly to do this whole LU factorization and then solve this Ly equals b and then use that to solve ax equals y. Yeah, that sounds like a long process. But keep in mind, this is a 2x2 matrix that we're working with. In real life applications, like you read in the book, you're dealing with much larger systems of equations. You could have 100, a matrix that's 100 by 100, or even 1,000,000 by 1,000,000. These ridiculously large matrices that show up in real life applications, you need ways to efficiently solve them with a computer. And some of your traditional techniques that you learn in linear algebra just really aren't going to work anymore. Okay, when you try to implement those kinds of things in a computer, they're just too slow. All right, so this is just kind of leading up to some of the main ideas of this chapter that tells us how we can solve systems of equations using numerical methods and kind of avoid some of those drawbacks that you have to the slower linear algebra approaches that you may have learned. All right, so that does it for this part of Chapter 7. Next week, we're going to get into the rest of Chapter 7. We won't get through the whole thing because, like you've seen, it's a pretty long chapter. But we'll start to talk a little bit more about these solution techniques for systems of equations.